So we have no time to, so we start with the lecture and then there will be a seminar, so without quiz. I think it's time to start. Давайте, наверное, окей, sit down, Kathy. Давайте я напишу тему, окей. Okay, hello everybody, and now we start the new course. So this is lecture number 1. Okay, Introduction to Differential Equations. So I will try to present some necessary notions, definitions concerned with differential equations, and maybe describe some problems, show some problems raised on this way. Okay, so we will start with definition. Definition number 1. Let f of x be a function defined on an interval. X is between a and b. A and b may be infinite. They may denote infinity. Okay, so defined on I. Y equals f of x. And so by ordinary differential equation, we mean a function involving x and the derivatives of our function f small. A function f capital, call it f capital, depending on several variables. I will call them x, f of x, then f prime of x, and so on. And the nth derivative of f equals 0. So this function. Okay. And so I'd like to do some remarks. So note 1. In our course, we will speak about ordinary differential equations. So we will deal with ordinary differential equations rather than partial differential equations. So ordinary differential equations is the theory of differential equations concerned with functions of a single variable. And partial differential equations describe the behavior of functions of several variables in terms of partial derivatives. So in our course we will speak about ordinary differential equations, and so usually I will omit this word. So I will speak about differential equations, and by this I will mean ordinary differential equations. And note 2. Note 2. In writing a differential equation, we usually replace f of x by y. So we usually use symbols y equals f of x. So f of x is replaced by y, then f prime of x is replaced by y prime, and yn will be the nth derivative of f. And so we will consider differential equations in the form f of x, then y, y prime, and so on, yn. equals 0. This is the general form of a differential equation. This is number asterisk. Okay, well, so let it be 1. Maybe it's better. Equation number 1. Right. An example. So we may consider differential equation of the form f, so x times f of x plus maybe f of x squared minus 7 equals 0. And so, of course, it is more convenient to use y and y prime rather than f of x, right? So this differential equation will be rewritten in the form xy plus, so let it be f prime. Sorry, f prime squared minus 7 equals 0. So this is an example of a differential equation. Well, okay, the next definition number 2, let it be, so I will use this space. An order of a differential equation. Okay, so just a moment. Okay, the order of a differential equation. So usually I will use an abbreviation differential equation. So DE stands for a differential equation. DE, or so I will denote differential equation by DE, or ordinary differential equation, ODE. ODE. Okay, so the order of ODE is the order of the highest derivative involved in this function, in the equation 1. So is the order of the highest derivative involved in the equation 1. Okay. Let's go to our example. So what is the order of this differential equation in our example? Do you know what is the order of the differential equation? The order is the order of the highest derivative. What is the highest derivative involved in this equation? So 1, right? The order is 1, right? This is the first order differential equation. Okay, and what about, so example 1, the next example. If we consider something like y2 primes minus y2 primes plus y prime, so minus y plus 5 equals 0. What is the order of this differential equation? No. So the actual, right, so actually the order is 1, because y2 primes is not really involved in this equation, right? It can be eliminated. And so the order is also 1. So be careful with this. Okay, well, and now let's discuss about solutions of differential equations. So, так, а где же тряпочка-то? Where is the cloth? Ah, okay, it's here. Well, thank you. Okay, so the next definition, a function y equals f of x defined on an interval I is called an explicit solution of one of our general differential equation, this one, if it satisfies for all x from the interval. So this means that if we substitute this function into our general differential equation, we will get an identity in x. And so the next example, let's try to check whether the given function is the solution of the given differential equation. Okay. So example, the next example. Verify that the function defined by y equals x squared for x. So this is our interval. It can be infinite. So for all x, for every x on the real line, on the entire real line. So verify that this function is a solution of the differential equation, this one, y2 primes cubed plus y prime squared minus y minus 3x squared minus 8 equals 0. What is the order of this equation? This one? 2, right. This is a differential equation of order 2. Let's check whether this function is a solution of this differential equation. Okay, so to do this, we should find the derivatives of this function and substitute them into our equation. So y prime will be 2x and y2 primes is equal to 2. Next, let's substitute these functions into our equation, and we will get the following. So we will get 2 cubed plus 2x squared minus x squared, okay, minus 3x squared minus 8. Let's compute. Okay, it is equal to, so 2 cubed minus 8 will give us 0, right? Next, we have 4x squared minus x squared minus 3x squared is identical 0. So we can see that we have an identity, right? This function turns our differential equation to an identity in x. So this proves that y equals x squared is a solution of the given differential equation. Okay, well, now let's discuss implicit solutions of a differential equation. So this function is an explicit function because it is given, so it is solved for y in terms of x. So this is called an explicit function. But sometimes we deal with implicit functions. Implicit functions are given by a relation f of x, y equals 0. This is an explicit function, right? And sometimes in what follows we will obtain solutions of differential equations in the form of an explicit or of an implicit function, and we should be able to check whether an implicit function is a solution. Okay. Oh, sorry. don't want to remove it. I want to save this general differential equation. Okay. Okay. To check whether this implicit function is a solution of this general differential equation is much more difficult, right? Because so sometimes it is not easy or impossible solve this equation for y in terms of x. So sometimes it is not easy or impossible to find a function g of x such that y equals g of x. So this is a problem. Okay. But let's consider an example, and then I will give some comments concerned with this problem. So example number 4. Okay. Example number 4. If we want to check whether the function, implicit function f of x y equals x squared plus y squared minus 25 equals 0 is an implicit solution of the differential equation given by this function. So it is y prime plus x equals 0. Let's check whether this function is a solution of is an implicit solution of this equation. Okay. To do this, let's try to solve this equation. So this equation can be solved, but there are two functions. So the equation f of x y equals 0 has two solutions. So we can solve for y in terms of x in this form, or y equals minus root 25 minus x squared and then if we find the derivative, so if we consider, for example, this part, this solution, then we may try to find the derivative of x. It will be equal to minus x over root 25 minus x squared. And then let's substitute into the equation y prime plus x equals 0. Okay. Let's consider this. Let's substitute it, and we will get the following: root 25 minus x squared times negative x divided by root 25 minus x squared plus x. It is identical 0 for x between, so if x is between negative 5 and 5. X can't be equal to 5, or it can be, the absolute value of x can't be greater than 5, because the square root cannot be negative, so the expression under the square root can't be negative, or we can't divide by 0, so it is true only for this axis, right, these values of x. But sometimes it is difficult to solve this equation. How should we proceed if we can't solve? Right, we may try implicit differentiation. So we should consider, so using this example, we should do the following. Minus 25 equals 0. Let's find the derivative of y using implicit differentiation. So we differentiate with respect to x, so the derivative of x squared will be equal to 2x, and then the derivative of y squared is 2y. So this is the composite function, and we should use the chain rule to differentiate y squared, right? 2y multiplied by the derivative of y, right, equals 0. And so if we divide by 0, we get the following: y prime plus x equals 0. So starting from our equation, we get the required equation, right? So this proves that this implicit solution satisfies this differential equation, right? It seems to be correct, but sometimes if we operate in this way blindly, we may come to some contradiction like the following. So suppose, for example, we want to check whether this implicit function satisfy this equation. If we proceed in the same way, we will get the same equation, right? So we will get, if we differentiate both parts, or if we differentiate implicitly, we will get y prime plus x equals 0. The same equation, but this implicit function doesn't define a function, right? It's just a point, and so we can't state that this differential equation is satisfied on some interval. Okay, so we should give a. I will try to give a correct definition of an implicit solution, having in mind this contradiction, right? So I will use this space. Okay, definition number 4. Okay, so a relation f of x y equals 0 will be called an implicit solution. Of 1 on an interval if, so requirement number 1. So this relation should define implicitly a function. So there exists a function y equals g of x defined on this interval, right? Okay, we may not find it explicitly. We need not find the explicit formula for this function, but we should be so we must be sure that it exists. So we should verify in some, maybe using some technique to prove that this function exists on this interval. And the second requirement is that g of x should satisfy our equation, right? Okay. Well. Okay, and now we will discuss the general solution of an ordinary differential equation. So general solutions. Okay, I think I may use this space, right? This part of the blackboard, right? Is it okay? So general solution. Okay. So let's start with some discussion. So in calculus, you have already encountered the differential equations when you when you were finding the integrals of a function of functions, right? So in calculus, you solve differential equation in this form. So given a function f of x, you tried to find the integral, the antiderivative of this function, the set of all antiderivatives of this function. Right, and this is the same as to solve the following differential equation. So given a function, find this problem can be reformulated in the following way. Given a function f of x, solve this differential equation, y prime equals f of x. So to find the indefinite integral is the same as to solve a differential equation, right? And we know that the set of all solutions, just a moment, is given by, so it will be some particular function, let it be, so I will denote some particular function, let it be f of x plus c plus some constant c, right? So you can see that the first order differential equation involves a constant, one constant c, right? If we have a second order differential equation, for example, let's consider an example. So y prime equals, let it be x, right? Then the solution will be x squared half plus c, so one constant. Next, if we consider so the second order differential equation, we will get, so if we proceed step by step, we will get y primes first. We can find y prime first. It will be equal to x squared half plus c, and then by integrating twice, we will get y, which is equal to x cubed over 6 plus cx plus c1 maybe. So we can see that the second order differential equation involves two constants of two arbitrary constants, right? And we can make a conclusion that the number of constants depends, the number of arbitrary constants depends on the order of a differential equation, right? But this is not true. This conclusion is not correct. There are some counterexamples. Okay, so first, if we consider something like y squared plus y prime squared equals 0. This is a first order differential equation. Okay. But it can be satisfied only by a function y equals 0, identical 0, right? No other function will satisfy this equation. So this is a first order differential equation, but the solution involves no constant of integration, right? No constants of integration. Well, and so example number 2, if we consider something like y prime squared equals -1, so this differential equation has no solutions. On the other hand, if we have something like y prime minus y times y prime minus 2y equals 0. So this is a first order differential equation. But it has two one parameter families of solutions. So if we solve this, so we will try to solve differential equations on our seminar, but now I will give an answer. So the solution of this equation will be given by, so we know that the function, the exponent e to x will satisfy this equation, and if we multiply it by any constant c1, this will be also a solution of this equation, right? And a little bit later we will be able to prove that this formula describes all the solutions of these equations, right, for an or arbitrary constant c1. And at the same time, if we try to solve this equation, so the product is equal to 0. So this takes place if one of the factors is 0. So the first factor is 0 or the second factor is 0, right? So this is the one family of solutions, and the second family of solutions will be given by c2 times e to the power 2x. Okay, well, so the first order differential equation has the family of solutions involving two arbitrary constants. So this also contradicts our hypothesis, that our conjecture, that the number of arbitrary constants depend on the order, right? But so these are just some okay, so in what follows we will consider the differential equations for which this will be true. So in our classes this statement will be true. So the number of constants will depend on the order, will be equal to the order of differential equations. So you should have in mind, of course, this unordinary, unusual cases, right? Unusual situations, right? Okay. Will we have a break? Now I think it's time to have a break, right? Let's do it. Okay. So I will use this space. Okay, so based on our preceding discussion, we will define a family of n-parameter solution. So n-parameter family of solutions. Okay, so the functions defined by f of x, c1, c2, and so on, cn, of the n plus 1 variables will be called an n-parameter family of solutions. So is an n-parameter family of solutions. Okay. If our general differential equation, so if our differential equation is satisfied for any choice of the parameters. So if we choose some values for the parameters and fix them, right, is satisfied for each choice of a set of values. Okay. And for the classes of differential equations we shall consider, we can now assert that a differential equation of the nth order has an n-parameter family of solutions. So we will consider differential equations that of the nth order that has an n-parameter that have an n-parameter family of solutions. Okay. And now the question is how to find a differential equation given an n-parameter family of solutions. So sometimes we need to solve this equation, solve this problem. So problem how to find differential equation one given a family of solutions and parameter family of solutions. Okay. So to solve this problem, we should have in mind that we are given a family of an n-parameter family of solutions. So so our function y equals f of x, c1, c2, and so on depends on n parameters, but our resulting differential equation will not involve any parameter. So we should eliminate these constants, these parameters, when solving, well, trying to answer this problem, right? Okay. So the example. Find a differential equation whose one-parameter family of solutions represents a family of circles with centers at the origin. A family of circles with centers at the origin. So we are not given an exact equation like this, but we have a description of these curves, and so having this description, so the family should be the family of circles centered at the origin. The equations of these circles given by x squared plus y squared equals c, so you can see the constant c. And now to create a differential equation with this solution, we should just differentiate this equation implicitly, and we will get the following. We will get 2x plus 2y prime equals 0. And so the required equation will be y prime plus x equals 0. Right? So this is example number 1. And example number 2. Okay, so example 2 will be, so I'll have a look. So given this equation, so this family, one parameter family of solutions, find the corresponding differential equation. Okay, so the problem is how to eliminate this constant c. What shall we do to eliminate c?
We need c on one side of the equation.
Okay, right. So what shall we do to eliminate c? Okay, so the square root. So the first idea is to take the square root, root 2x. Okay, but so the problem is the expression y minus c may be negative, right? But if we take the square root, we will so we will have a restriction, right? So y minus c should be positive then. Or differentiate, right? Instead of this, let's differentiate the original equation. So differentiated implicitly, it will be 2 times y minus c times the derivative of the inside function, so times the derivative of y prime, equals 2. We can divide both sides by 2, and we get this. What shall we do next? Let's compare. So given this and this, so this is not the required differential equation because it depends on so it involves a constant, but it mustn't. It should not be a constant in the differential equation. What shall we do? So, but we have this. Let's square, right. Let's square both parts. Y minus c squared times y prime squared equals 1. And then we can substitute 2x for y minus c squared. And so we get the following. 2x times y prime squared equals 1. So this is the answer. Well, okay. Now let's discuss a general solution. So general solutions. A general solution of the differential equation and particular solutions. And in what follows, maybe not today, we will discuss singular solutions. So this should be discussed. Okay, so traditionally, an n-parameter family of solutions is called a general solution. And a particular solution can be obtained from a general solution by substituting some values for arbitrary constants. Right? If we give values for arbitrary constant, then we will obtain a particular solution from a general solution. But this is also not correct. This is not correct. Because sometimes there are particular solutions that are not obtainable from a general solution. Okay. Let's consider some counterexamples, and then we will discuss their correct definitions. Right? So, for example, given an equation y prime minus y equals 0, we can prove that y equals c e to x is a general solution. So this is a one-parameter family of solutions. This represents a general solution. And if we substitute, for example, c equals -2, we will get a particular solution. a particular solution. But we have some other examples, so let it be example number 3. So let's consider the first order differential equation, y equals xy prime plus y prime squared. Okay, so this differential equation has the one parameter family. So one parameter family of solutions. Is y equals cx plus c squared. Let's check that it is actually a solution. Let's check that this is a solution. So this is the first statement. To check this, we should find the derivative. It is equal to c, and substitute both y and its derivative into the original equation, right? We will get the following: cx plus c squared equals, and we should check this, x times c plus y prime squared plus c squared. So identity in x. So this is a solution. This is a one parameter family of solutions, and this is a first order differential equation. And so it may seem that this formula describes all the solutions, but however, we have a solution, a particular solution given by this formula. Let's check that this is also a solution. So y prime is equal to minus x half, and let's substitute y and y prime into the original equation, and we will get minus x squared over 4 equals, so we should check this, x times minus x half plus x squared over 4. So this is correct, right? Correct. So this is a particular solution, but it is not included in this family. So it is not correct to call the n parameter family of solutions a general solution. So a general solution must include all the solutions of the differential equation, but not only given by this n parameter family. Well, and okay, so this will be so definition number, so it's definition number 5, definition number 6. A solution of a differential equation will be called a will be called a general solution if it contains every particular solution. So we should start, sorry, with a particular solution. So a solution of a differential equation will be called a particular solution. A particular solution. If it satisfies the equation and does not contain arbitrary constants. Okay, and definition number 7. And then parameter family. Okay, so the set of all, it will be better to call it, so the set of all the solutions, right there, the set of all possible particular solutions is called a general solution. Of 1. Okay. And now let's discuss initial conditions, right? Initial conditions. So since there is a finite, infinite, so there is an infinite number of ways of choosing the n parameters. Sometimes we need to know not all the solutions, but a particular solution satisfying some conditions, some initial conditions, right? Okay, and for example, suppose we observe an experiment that at time t equals 0, so example, it will be an example. We observe an experiment that at time t equals 0, a body is 10 feet from an origin and is moving with a velocity. So at this time, a body is 10 feet from the origin and is moving with a velocity of 20 feet per second. Okay, and so if we describe the, for example, if we describe this motion, we get the following: x equals. So suppose the motion of this body is described by the following equation: two parameter family of solutions. Let it be, right? So what is the differential equation? So to find the corresponding differential equation, we should differentiate 2 times, right? X prime equals 32t plus c1, and x2 primes is equal to 32. So this motion describes the motion of a body with a constant acceleration, right? Acceleration, and then so we get this 2 parameter family of solutions, but we want to know the motion of a body which at time 0 is 10 feet from the origin and moving with this given velocity. So our goal then, so after we solve this equation, our goal is to find the constants having this initial condition. So to do this, we should substitute, so at time t equals 0, so we should substitute 0, and then we will find that x of 0 should be equal to 10, and from the other side, we can substitute 0 into this solution, and we will get that it is C2. So we have found C2. And then we know the velocity at the initial at time equals 0. So we should differentiate this two-parameter family, and we will get. So this is the. Sorry, it is found. It is already found. This is the velocity, and at t equals 0, it must be equal to 20. So we should find. We may find x prime of 0 from this equation. It is equal to c1, and on the other side, it is equal to 20. So C1 should be equal to 20, and so the final answer is the following. X of t is equal to 16t squared plus 20t plus 10. Okay. So this is our answer, and now I'd like to give the general definition of the solution of a differential equation with the given condition. With the given initial conditions. So, definition number 8. So, the n conditions which enable us to determine the values of the arbitrary constants. Determine constants. In an n-parameter family, if given in terms of one value of the independent variable, are called initial conditions. In a general solution, maybe it's better. In a general solution. So, or no, it depends. So it is, of course, n-parameter family. In an n-parameter family. So if given in terms of one value of the independent variable. So, for example, we are given initial conditions for this value of the independent variable. So, if given in terms of one value of the independent variable. Are called initial conditions. And today we will try to solve differential equations, to find particular solutions using initial conditions. Okay. Right. And so on the next class we will have a seminar, but I will describe the method of solving particular class of differential equations. So today we will discuss separable differential equations. and I will give a general theory of solving these equations, and on the seminar we will try to use this method for solving given differential equations. Okay, so today during the seminar we will consider solving the method of solving separable differential equations. Okay, so separable differential equations. Okay, a first order differential equation of this form is called a separable differential equation. If the function f of xy can be factored, can be represented as the product of two functions depending on x and y separately, right? Okay. So if the function can be factored as follows. This is the product of two functions. The first one depends on x only, and the second one depends on y. And next, we will try to solve this differential equation. To do this, we will first represent y prime as the ratio of two differentials, dy and dx. It is equal to g of x times h of y. Then we want to separate variables. This means that I want to gather all the expressions involving y in the left-hand side and the expressions involving x in the right-hand side. So I will divide by h of y and multiply by dx. Okay, so we get this. The next step is to integrate both parts. So this is the first step. Represent f of xy as the product of two functions. Step number 2 is represent y prime as the ratio of differentials. Next, separate variables. And number 4, step number 4, integrate both parts. Then I will write plus c. We need not add constant if we have integrals, because an indefinite integral is the set of all antiderivatives. But I will write this to emphasize that that an arbitrary constant appears in this integration. Okay, and this will give us a non-parameter one parameter family of solutions. But is that all? Is there some problem with this? Is there any problem with this solution? So, is that all? Haven't we lose some particular solutions or not? Is it correct to divide by h of y, for example? Can we divide by h of y? But right. We should consider particular cases when h of y equals 0. This will give us particular solutions, because if we have some roots, so suppose we're trying to solve this, and we find some roots. Then all these roots will satisfy our original equation, this one, y prime equals the product, this one, right? Let's try that all these roots satisfy this equation. Let's check this. So what is y prime? So if we consider, for example, y equals yi, so this is a constant. If we differentiate it, we will get 0. Now, if we try to check whether this is a solution, we should substitute into the original equation, this one. So we have y prime is 0 equals g of x times h of yi. But what is h of yi? It is 0 because these are roots, right? So it is 0. So since this particular since these constant functions satisfy the original equation, they are particular solutions. And when we write the answer, we should gather together all the solutions. So we should form the answer from the one parameter family of solutions and particular solutions found from solving this equation. Okay. Okay, so we have time, and then I will try to show you how to solve differential equation, separable differential equation. I will consider 2 examples. The first example will be, so to solve y prime equals x, and example number 2 is to solve y prime equals y. Okay, so for the first example, so I think it's easy, and you know how to solve this from calculus, right? Using integration. But if we use the technique of integrating separable differential equation, we should represent y prime in this form, then separate variables, so dy equals x dx, and then integrate both parts, and we will get the answer y equals x squared half plus c. Well, I think it's clear. But the equations of this form were not studied in calculus, right? Let's try to solve this. First, we should represent y prime as dy over, as the ratio of differentials, dy over dx equals y. Then separate variables. So we should move y to the left-hand side, right? To the left. Dy over y equals dx. And then to integrate both parts, and we will get the following. The natural logarithm of y equals x plus c. Okay, so I will write y is not 0, so this is true if y is not 0. And after all, we should consider this particular case. So we should consider the roots of this function. It has the only root y equals 0, so we should consider this root, and we should include this particular. So this is a particular solution, as was proved before, and we will include this in the family of solutions, in the general solution. But now let's discuss this. So we are done. We have obtained an implicit function as a solution of this original equation, right? So we may leave our solution in this form, but we may eliminate logarithm, right? And we may solve this equation explicitly for y in terms of x. What shall we do? Okay, so if the logarithm of y is equal to x plus c, then this means that the absolute value of y is equal to e to the power x plus c. Yeah. But this can be represented as e to the power c times e to x. Okay, and we may call this so since c is an arbitrary value, then e raised to the power c is an arbitrary positive value. Call it c1. It is positive. Okay, and so since the absolute value of y is equal to, so I will use this space, right? So we have the following: the absolute value of y is equal to c1 times e to x, where c1 is positive. Then y is equal to plus or minus c1 times e to x, where c1 is positive. And in addition, we have a particular solution y equals 0. Is it possible to simplify this answer? Kathy, what is your opinion? Is it possible to simplify this answer? You know, to simplify. So this is the answer: plus or minus c1, where c is positive, c1 is positive, times e to x, and this particular solution. So this is the answer. How to simplify it? Not use plus or minus c1 and c is positive. So if we use c2, if we introduce the new constant c2 and write y as c2 times e to x, then this family will include both families, plus c1 or minus c1, and it will include this particular solution. So our particular solution can be included in our general one-parameter family. So this is the final answer. So that's all, I think. So I can finish my lecture. Next we will have a break and we will have a seminar.